introduce Federico.
Okay, well, first of all, I would really like to thank the organizers for the opportunity and the honor to speak here. Trying to make it a little warmer in here with my cover page. So I will tell you about linearity in the tropics. So this is the subject of my talk. There's a little tropical line going surfing in Hawaii. So that's the subject of my talk. I think this is where we should have the meeting next time, actually. That's Pacific, right? Okay, so let me start by just giving you a brief summary of what I plan to tell you about. So the first thing that I would like to do is just tell you some general things about tropical geometry, some very general things of what the subject is about. And then I will start telling you about the main subject of my talk, which is tropical linear spaces. Okay? And I will tell you that there's kind of two natural cases that one needs to consider for tropical linear spaces. There's a constant coefficient case and an arbitrary coefficient case. And I will tell you how that goes. And as you can see, the main summary of my talk is what I have in the little box there. So my point is to tell you that tropical varieties are not simple objects, and that even in a relatively simple case, which is the case of tropical linear spaces, there is already a lot of very rich and interesting structure that we know some things about and we don't know some things about. So first, just a very general introduction to what tropical geometry is about. And I should mention that tropical geometry means different things to different people. Somehow, several different schools of thought have been converging into similar ideas that are only starting to be developed into a solid foundation. And so the point of view that I'm going to take is the following. I'm going to be looking at tropicalizing algebraic varieties. And so what that means is that I take an algebraic variety and I tropicalize it into a tropical variety. I have to apologize that I noticed there was a typo in my abstract. I spelled tropicalization with a Z. I got it right this time. So what's the idea? The idea is that you have an algebraic variety and you want to understand things about it. And sometimes what you can do is take the variety, tropicalize it, and this tropical variety is going to preserve some of the information about the original variety. Okay? Now, of course, the point, if this is to be useful, is that the tropical variety is a simpler object. And even though it's a lot simpler, it still gets to keep some of the information about B. Okay? One sense in which a tropical variety is simpler is that it's a polyhedral complex, and that means that there's a lot of combinatorial tools that we can apply there. Okay? If you're used to thinking about toric varieties, there's the analogy of how a lot of the properties of a toric variety are controlled by the corresponding polyhedral fan. And this is a good analogy to keep in mind here. Okay? We want to derive properties of the algebraic variety by getting them from the tropicalization. And again, like I said, there's many different ways of approaching this, and the way that I will be talking about is through Puiseux series, okay? So what's a Puiseux series? A Puiseux series is something that is kind of like a power series, okay? Except that I'm going to allow the exponents to be arbitrary rational numbers. And there should be kind of a lowest exponent, and then it should be a discrete set of rational numbers that has a common denominator, okay? So these are kind of technical things, but it's, for the purposes of this talk, it's safe to just think that this is just a series, okay? We just allow some rational exponents, okay? Now, the key property of why I want to talk about the field of Puiseux series, there's two things that I need. First, if we're going to be doing algebraic geometry, it's going to be convenient to choose an algebraically closed field, and so this one has that property. And the other key property that I want is that I want to have a valuation. And the valuation is the degree function that takes any Puiseux series and maps it to the lowest exponent. Okay? So now, like I said, my intention is to tropicalize varieties, and I can do this in two ways. I can do this by tropicalizing the points of the variety, or I can do it by tropicalizing the equations of the variety. So let me tell you how you do each one of these things. So to tropicalize points, well, basically, if you have a point in k to the n, so it's just an n tuple of Poisson series, and you just take the degree of each component. Okay? So for example, if I have here a pair t squared plus 3t cubed, etc., and then t to the 1.5 plus etc., that gets mapped to 2, 1.5. Okay? That's how you tropicalize a point. How do you tropicalize a polynomial? What I'm going to do is that I'm going to take the usual operations of addition and multiplication and turn them into the operations of taking the minimum and adding, respectively. And then whenever I see any constants, and remember, a constant here is a Poisson series, okay, then I'm going to take that and map it into its degree. Okay? So for example, here is a polynomial in x, y, and z. Okay? And so what I do is, first I see a constant, and so I map it to the valuation, so that becomes a 1.5. Then x squared, it's x times x, so that gets mapped to x plus x. Okay? And so that's how I get this 1.5 plus 2x. And then this plus right here becomes the minimum. Okay? And then the 2yz becomes, the 2 has valuation 0, so it disappears, and then yz becomes y plus z. Okay? So that's how I go from a classical polynomial to a tropical polynomial, which is just some piecewise linear function like this one. Okay? Now, why is this good? Well, the first thing that I'd like to tell you about this is that basically we can go either route. I could have either tropicalized the equations or tropicalize the solutions, and I'm going to get the same answer. Okay? And this is the fundamental theorem of tropical geometry, which says the following. If I start with an ideal, and I consider the corresponding variety, then the tropical variety is defined to be either one of these two things which are equal to each other. So the first thing you can do is take each polynomial equation in your ideal, f of a equals 0, and you just tropicalize that equation. Okay? And so f becomes trop f, and then for a reason which I think will become clear in a second, instead of saying equals 0, you want to say that tropical polynomial is achieved twice. Remember that a tropical polynomial is going to be a minimum of a bunch of things. And so that condition over there just basically is going to say that a minimum of a certain number of terms has to be achieved at least twice. Okay? So that's one thing you could do, tropicalize the equations. But the other thing you could do is just go to the variety itself and take each one of the points in the variety and map it through the valuation. Okay? And that's the second alternative. If you just take the degree of all the points in your variety and you take the closure of that, then you get the same object. Okay? So this is the fundamental theorem of tropical geometry. Okay. So just a quick example. Here's a variety. It's as you can see, this is just a linear equation in x, y, and z. Okay? And when I tropicalize it, I can either tropicalize the defining equation or I can tropicalize the solutions. Okay? And what I'd like to argue very quickly is that at least one of the directions of this equality is very easy. Okay? Let's see why the second set is contained in the first set. Let's suppose that you take a point in the second set. So the way you obtain that is by taking a point in your variety, x, y, z. That point satisfies this equation, right? And now you're going to take the degree of that, okay? Now, if you look at this first summand, if big X has degree little x, then when I multiply by t to the negative 3 plus 2, it's going to have degree little x minus 3. Okay? Then this guy is going to have degree little x plus 1, and this guy is going to have degree z. Okay? Now, if you add up three things and they add up to 0, then you must have canceled the lowest term. And that means that the lowest term has to appear at least twice there. Okay? So that part is very easy to see, that 2 is contained in 1, and the other direction is a little bit harder, but it's also true. Okay. Okay. So this is the definition of tropicalization. It's a very simple definition, and maybe it's surprising that such a simple definition can be so useful. Okay. If we want to carry this out, if we want to apply this technique, then there's 2 things that we need to ask ourselves. The first thing is, what does the tropical variety know about the variety? And the second thing is, what do I know about the tropical variety? Right? So let me talk about the first question quickly. What does the tropical variety know about the variety? Well, as you can see from the definition, we lost a lot of information in tropicalizing. But yet there's a lot of information that we didn't lose. And this was the key insight of, for example, Michalkin, who proved that you can compute the Gromov-Witten invariance of CP2 tropically, and you're going to get the same answer as you do classically. Okay? There's a real analog of that in genus 0 that also works out, and this was done by Walshinger. There's a very recent paper of Cavalieri, Johnson, and Marquig that shows that, for example, you can also compute double Hurwitz numbers by tropicalization. And if in the classical question and the tropical question are going to give you the same answer. Okay? And of course, this is a key step and a delicate step where you really have to know what are the right questions to ask that you can tropicalize and say something interesting about. Okay? The second question is, what do we know about tropical varieties? And this is something that really we do not know so much about. So there's only a couple of very general theorems. So the first theorem is due to Bieri and Groves, who showed that if your variety that you start with is irreducible, then the tropical variety, like I said, it's a polyhedral complex. And their theorem is that, first of all, it's pure, meaning that all the, I mean, what's a polyhedral complex? Well, it's what you obtain by gluing a bunch of polyhedra together. And their theorem says that all the polyhedra that you glue together have the same dimension. That's what it means to be pure. And also, this complex is connected in codimension 1. So you can walk from any maximal face of dimension D to any maximal face of dimension D by only crossing faces of dimension D minus 1. There is a topological statement saying that the links of tropical varieties have only top homology if the variety is shown. And this is a definition that, as I understand it, was just kind of customized to make this theorem work. And it's a definition that is hard to check. I mean, it's a very nice theorem, but it's hard to work with it. Okay. Now, in special cases, especially in the special case of curves, this is the case that is best understood. Okay? And there's a lot of very nice work of Fomin, Gatman, Michalkin, a lot of people about tropical curves. Okay? But again, the point is that, like I said, you tropicalize because you want to work with a simpler object, and tropical varieties are simpler, but they're not simple. They're not trivial, and that's basically what I want to talk about today. Okay? So let me start by just giving you some quick examples of tropical varieties so you can see what they look like. I have to apologize that picture is upside down. If you know something about tropical geometry, you might know that there's a debate whether we should be using minimum or maximum. And I used the wrong ones, and I just realized 5 minutes before the talk, so anyway, so what does a hyperplane look like? Okay. Well, an ordinary hyperplane just looks like some equation a1x1 up to anxn equal to 0. Okay, so when you tropicalize, then we get something that looks like this. The minimum of xi plus ai is achieved twice, where each little ai is the evaluation of the big ai. Okay? So for example, a tropical line in TP2 is this one. The minimum of x minus 3, y plus 2, and z appears twice. Okay? And so, of course, you can imagine that this is going to have 3 pieces because you need to decide which 2 of the 3 guys are going to be the small ones, that are equal to each other. Okay? So for example, now I should say that these are all projective pictures. If I add a constant to all the variables, nothing is going to happen. I'm going to stay in the variety. So I'm identifying the point A, B, C with the point A minus C, B minus C, 0. I'm just assuming that the last coordinate is 0. And then, for example, this ray is where x minus 3 is equal to y plus 2 and is less than 0. Okay? So that's what it looks like, and those are the three pieces of the tropical variety. Okay. In general, the tropical hyperplane, well, this is the next example. In a three-dimensional one looks like this. You see it's already a little bit complicated. I don't know if you can see it very well, but it is 6 quadrants coming out of a point. Okay? This is the polar fan of the tetrahedron. Okay? And in general, a tropical hyperplane is just the polar fan of a simplex. Okay? What do tropical conax look like? Well, this is just to show you some nice pictures. As in the classical case where a conic might be an ellipse or a hyperbola or a parabola, well, here you have different types of conics, and these are two of the different types. Okay. Now let me show you a tropical line in TP3. Okay. TP3 is the tropical projective space, right? So let's say that the classical line is the row space of that matrix. Okay. And the tropical line is just the topicalization. So again, there's two things that I can do. I can either do it with the equations or with the points. Okay. So one thing that I did ahead of time was just compute the equations of this linear space, and then I tropicalized those equations, and that's what I got, those 4 things. And then the picture looks like this. Okay. But then we can also check that you can do it by tropicalizing points. So for example, the first row, if you look at the valuation of the first row, it's 0, 1, 2, 3. And so that should be on my line somewhere, and it's right here. That's -3, -2, -1, 0. Okay. So anyway, that's what a tropical line looks like, and you should be seeing this. It's actually important that you see this as a 3-dimensional picture, where there's 4 directions, and one of the 2 directions are kind of like this, going that way, and the 3 and the 4 directions are like this. I don't know if this is making any sense. So 1 and 2 are like this, and 3 and 4 are like this. Okay. It's really a 3-dimensional picture, and that's important. You'll see in a second why it's important. Okay. Okay, and so, like I said, the goal is basically to tell you what we know about tropical linear spaces, and these are some examples. These are 3 examples of tropical linear spaces. Okay. So the next thing I'll tell you is what do tropical linear spaces look like when you have constant coefficients. Okay? So the first thing I'll show you is that as soon as you start to ask that question, you run into matroid theory. Okay? And then I'll give you a quick crash course in matroid theory so that I'm able to state what the main theorem is. Okay? So in the constant coefficient case, what does this look like? We have a linear subspace V. We want to describe the tropical variety. Okay? So the way that goes is that for each equation satisfied by my linear space, which looks like, I don't know, A1 xi1 plus AK xik equals 0, I tropicalize that equation. But it's very important through this whole section 1 that you remember that all my coefficients are constant, meaning that they have valuation 0. Okay? So that means that when I tropicalize these coefficients, A1 up to AK, they disappear. And all I get is the minimum of, I guess I had been using little x, so you should think of these as xi1 up to xik. Okay? So again, just to be very explicit, here's an example. If L is the row space of that matrix, then to tropicalize it, the first thing I do is write out the equations. The equations of that line are, of that plane, sorry, are x1 minus x2 plus x3 equals 0, and x4 equals 2x3. And then I'm going to call the support of each equation a circuit. Okay? So for example, because I have the equation x1 minus x2 plus x3 equals 0, then I call 1, 2, 3 a circuit. Okay? You see that even though I wrote only 2 equations, I wrote 3 circuits because there's also a relation between 1, 2, and 4. Right? So you need to do this for every circuit. You need to check that the minimum of the numbers in that circuit appear twice. Okay? So for example, in this case, I need that the minimum of W1, W2, W3 appears twice, etc. Okay? And if you just do that carefully, you'll see that what you get is that line that I drew over there. Okay? So this is an example of a tropical line. So this is just repeating what I said. The tropical linear space is given by the points W in Rn, such that in each circuit the minimum is achieved twice. Okay? Now the next thing you should notice is that we basically lost all the coefficients, all the numbers, and all the data that we're using here is the set of circuits. Okay? The tropical variety only depends on the set of circuits, and this is exactly what's known as the matroid of the vector space. Okay? And I'll define for you in a second what matroid is, but you can think of a matroid as a set of circuits, and I could make the same definition for any matroid. The tropicalization, the tropical linear space of the matroid is given by the W's in R to the N, such that the minimum in each circuit is achieved twice. Okay? And so let me just give you a very quick summary of some basic things about matroid theory that we will need. Okay? So here's a little crash course in matroid theory, and this crash course is going to have 3 parts. Okay? So the first part is matroid theory version 1, circuits. Okay? Now, very generally, what is matroid theory? Matroid theory is a combinatorial theory of independence. Okay? There's a lot of notions of independence in mathematics. We have linear independence, algebraic independence, graph independence. And what this does is that it kind of systematically studies the combinatorial properties of those notions. Now, these 3 properties right here summarize the main features of all of these notions of independence. Okay? And again, as I say this, just think about algebraic independence or linear independence as a very concrete example. So I'm going to say that a matroid is a ground set E, which maybe you want to think of as a collection of vectors, and a collection of circuits, which you want to think of as dependent sets. Okay? Minimal dependent sets. And so the first 2 conditions are kind of trivial. You're saying that the empty set is independent, and you're saying that minimal dependent sets, one cannot contain the other because they're minimal. So really the only interesting condition of these 3 is this third one that says that if you have 2 circuits, C1 and C2, and they contain a common element, then you can take the union of these 2 circuits, take out that element, and that is also going to contain a circuit. Okay? And you can see this very concretely in the example that we saw before. I'm just saying if you have an equation like x1 minus x2 plus x3 equals 0, and another equation like x4 equals 2x3, and x3 appears in both equations, then you can just take those equations and eliminate x3. Okay? And you're going to get a third equation. Okay? And all of these notions of independence satisfy this very simple property. Okay? And so we call something a matroid if it's just a set of circuits that satisfy this simple property. Okay? One thing that I would like to point out is that I started by talking about the circuits of a vector space. Okay? And so, for example, this is the example that I gave you. But now, if you look at the equations of that linear space, those are exactly the linear dependencies between the columns of the matrix. Okay? So for example, the first equation says the first column of the matrix minus the second column plus the third column is equal to 0. And so you have 2 ways of thinking about this example. You can always think of a linear space as just the columns in any matrix representation of it. Okay? And as far as the matrix is concerned, this is the same thing. So why do we have a theory of matroids? Well, it's just a very general object that we can apply to a lot of things. Okay? For example, there's an easy theorem, just a toy example. There's an easy theorem that every matroid has a rank function. And if you translate to linear dependence, this gives you dimension. If you translate to algebraic dependence, this gives you transcendence degree of field extensions, things like this. Okay? So it's a very general machinery. And it's very well developed, so there's a lot of different points of view that we can use. There's matrix polytopes that we will talk about. There's lattices of flats that we will talk about. There's a very nice machinery of matrix that you can use to apply to all of these settings. Okay? But the main reason that we're going to care about matrix theory is that we're talking about taking algebraic geometry and tropicalizing it. And if you look at how that specializes to linear spaces, then you will see that basically this tropicalizes to sending linear spaces into matrix theory. Okay? It's kind of inevitable to arrive there. Okay? So here's matrix theory version 2, matrix polytopes. Okay? So you can also think of a matroid as being a collection of bases. Okay? So let's take our same matrix L over there. Okay? And now instead of saying what are the dependent sets, let's say what are the bases of the column space. Okay? So if you look at the column space, you see that the columns 3 and 4 are dependent, and every other pair is a basis. So the bases are columns 1 and 2, columns 1 and 3, 1 and 4, 2 and 3, 2 and 4. Okay? So those are the bases of my matroid, and now what I'm going to do is that I'm going to make a polytope out of them. And the polytope is obtained by taking each basis and making a 0, 1 vector where you put 1s where the basis is and 0 where the basis is not. Okay? So for example, I don't know, you take the basis 1, 4, well that gives you the vector 1, 0, 0, 1. Okay? And you just take the convex hull of those points. This is called a matrix polytope, and there I drew the example of what that matrix polytope looks like. Matrix polytopes arise very naturally in two very different places. One reason that matrices are interesting is because they appear very naturally in optimization. And if you think about approaching matrix theory from the point of view of linear programming, then this is the polytope where you want to do linear programming. Okay? So a lot of the theorems about it come from that point of view. But this is also very natural from the point of view of toric geometry, because if you take a linear space that gives you a point in the Grassmannian, okay, and you have a torus action on the Grassmannian, and if you look at the orbit of that point, if you take the closure of that, that's a toric variety. The corresponding polytope is this guy. Okay, and so this polytope is also very natural from the algebraic geometry, and the theorems come from these two places. And I should tell you, this is maybe my favorite theorem in matrix theory. It's a theorem of Gelfand, Goreski, McPherson, and Serganova, who developed this toric point of view. And they proved that a matrix polytope is essentially a polytope whose directions are exactly roots of the AN root system. Okay? So if you look at all the S directions of that polytope, they are the form EI minus EJ. The polytopes that you can make in this way are exactly matrix polytopes. And that gives you another point of view on what the theory of matrix is about. Okay? Now, why do we need this? The reason that we need this is that you can describe a tropical linear space fairly easily in terms of the matrix polytope. Okay? And the way you do that is that you say that a matrix is loopless if every element is in some basis. Okay? So for example, here we have that the bases are 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4. So that every element is in a basis, so the whole matrix is loopless. Okay? And now we're going to do that for each one of the faces of this matrix polytope. So for example, for the top face, you see that you have 1, 2, 1, 3, 1, 4. So that's a loopless face, and I color it green, let's say. Okay? So you see there's 3 faces that I colored green, but for example, in the face closest to you, the 1, 2, 1, 4, 2, 4 face, that is not a loopless face. So I don't consider it. Okay? And so the observation of Sturmfeld was that the tropical linear space is exactly the fan dual to the loopless faces. Okay? So you see that those three directions on the right-hand side are exactly the normal directions of the three loopless faces. Okay? And so if you want to study the tropical linear space, then you might as well study it in terms of the dual picture, which is the matrix polytope. Okay. Now, the other point of view that we're going to need is the point of view of a lattice of flats. Okay? And I think maybe the best way to do this is in an example. So I need to define the lattice of flats of a matroid. And the matroid that I'm going to consider is the collection of vectors given by the columns of that matrix. Okay? And as you can see, this is the root system A4. Okay? If you draw that root system, it's going to look something like this. Okay? And now I'm going to define a flat. And what a flat is just some linear space spanned by your vectors. Okay? So for example, you can consider every line spanned by a vector. And so you're going to get three flats. Just call them 1, 2, 3, 4, 5, and 6. But you also have some planes like the 1, 2, 5 plane. Yeah? And so that's called a flat also. Okay? So 1, 2, 5 is one of the planes that spanned. 1, 3 is another one of the planes that spanned. 1, 4, 6 is another plane, etc. Okay? So you look at all the different flats that you obtain, and you're going to make a poset out of them by ordering them by containment. Okay? So the picture over there is the vectors. This is the lattice of flats. It's a lattice if you put a top and a bottom element on it. And then what you're going to do is that you're going to consider the order complex or the chain complex of this guy. What you do is that you make a simplicial complex where the vertices are the flats and the faces are the flags, where by a flag I just mean you walk up the poset. Okay? So for example, I have a phase between 2 and 2, 3, 6 because I have a flag from 2 to 2, 3, 6. Okay? So this is how from a matroid you make a simplicial complex, which is the guy that I drew on the right. And there's a very nice theorem saying that this is a beautiful simplicial complex that has all the properties that combinatorialists like it to have. It's pure, it's shellable, and it has the homotopy type of a wedge of spheres. Okay? And we can say exactly how many spheres there are in terms of the combinatorics of the matroid. Okay? This is the Mobius number, which is easy to compute. So just to summarize, what I did is that I started with a matroid, and I made a simplicial complex out of it, and this theorem says that it's a beautiful simplicial complex. It has all the nice properties that we want it to have. And the reason that I introduce all of this is because the main theorem on tropical linear spaces with constant coefficients is that the tropical linear space is exactly that simplicial complex. This is a theorem joined with Carli-Kleivans. Well, that's almost true. The only thing is that, so our theorem is that you can take the tropical linear space of a matroid and then subdivide it to get this order complex that I just described. Okay? But of course, subdivision is not going to change your topology, which was our motivation. We wanted to understand the topology of tropical linear spaces. And what we found is that at least in constant coefficients, a tropical linear space is just a cone over a wedge of spheres. And we can say exactly how many spheres there are in terms of the combinatorics. Okay? So in a sense, this object couldn't be nicer. Okay? So that's the main theorem on the constant coefficient case. There's some other nice theorems about this. I think maybe I shouldn't say too much about them, except to say that when you look at the way this goes for concrete matroids, for example, you might have a favorite matroid like I don't know, my favorite vector configuration is a root system. And if you see how this definition looks for root systems, and if you study the tropical linear space of a root system, then in type A you see that you get the space of phylogenetic trees, and you can have some nice biology theorems coming out of this. It's kind of a nice unexpected consequence. And for any finite root system, there is a geometric interpretation of the thing that you get. So the first thing that I said is from work with Clivens and a paper by myself. And the second thing is joint work with Vic Reiner and Lauren Williams. But let me now go to the case of arbitrary coefficients. Okay? So the first thing I would like to tell you is that if you understand the constant coefficient case, then that really helps you understand the arbitrary coefficient case. Okay? Let's go back to the first example that I did of a tropical line. It looks like that. And there's a nice observation which says that if you take any tropical line with arbitrary coefficients, and if you just stand at a point and see locally what's around you, then what you're going to get is also a tropical linear space, but it has constant coefficients. Okay? So locally, we understand exactly what happens. So for example, here, if I look at the two vertices of my tropical linear space, then I kind of split it up into two tropical linear spaces that are simpler. Okay? Now, by what I said a second ago, each one of these simpler tropical linear spaces is dual to a matroid polytope, right? And so I have my matrix polytope on the right, my matrix polytope on the left. Okay? And the beautiful thing about this is that actually you can put these pictures together because these matroid polytopes come together to form a tiling of the main matroid polytope, which is the hypersimplex delta ND. So here you see it. These two guys come together into an octahedron, which is the hypersimplex. Which, by the way, this bigger thing is also a matroid polytope. So the main theorem about this is that if you want to study a tropical linear space with arbitrary coefficients, then these objects are basically in correspondence with the ways of taking a matroid polytope and subdividing it into smaller matroid polytopes. So this little table summarizes it. If you want to understand the constant coefficient case, then you go to matroid theory. And if you want to understand the arbitrary coefficient case, then you go into the theory of matrix subdivisions. Now, these matrix subdivisions actually also have several very natural geometric interpretations, but I think in the interest of time, I shouldn't say too much about them. But maybe one thing I will say is that there's this very nice theorem of Laforgue about this, which says that if you have a matroid polytope, and this matroid polytope is indecomposable as smaller matroid polytopes, then that tells you a lot of information about that matroid. It tells you that matroid can only be realized by finitely many linear spaces up to trivialities, up to projective transformations. Okay? And this is a pretty amazing condition because Menev's universality theorem tells you that general matroids have exactly the opposite end of the spectrum, where if you look at an arbitrary matroid and you look at the points in the Grassmannian that realize it, then these objects have arbitrarily bad singularities. Okay, so I told you that now we need to understand matrix subdivisions, and the problem is that this is something that there isn't really a theory for. I mean, this is a fairly new object. I think the first person to think about it was Laforgue and later Kapranov. And so maybe for the last few minutes, what I would like to tell you is just a little bit about some of the combinatorial aspects of matrix subdivisions. Okay. So for example, here is a matrix subdivision. So the big polytope is the hypersimplex 6, 3. Okay, so it's a polytope that lives in 6 dimensions. It has 20 vertices, and each vertex is obtained by choosing 3 1s and 3 0s and making a point, taking the convex hull. So for example, I claim that that guy can be subdivided into 3 matrix polytopes in the way that I drew it. This is a schematic picture because this really lives in 5 dimensions, but the subdivision looks like this. Okay? And these 3 matrices I'm describing to you in terms of these point configurations. So for example, matroid 1, 5 and 6 are the same vector. That vector is collinear with 3 and 4, and 1 and 2 are not on that plane. Okay? So I claim that's a matrix subdivision. Well, there's a lot of things to ask about this. First of all, where did I get the subdivision? Second of all, how do you know if I'm not lying to you? How do you check that this really is a subdivision? These are pretty complicated questions, actually. How do you construct these things? How do you verify if they really are subdivisions? How do you prove impossibility of subdivision so that you can use Laforgue's theorem? And one approach that we have considered is basically finding ways to measure a matroid in a way that is compatible with this picture, okay? In a way that behaves valuatively on the polytope. Okay. So I'm going to say that a function from all the matroids, let's say, a function from matroids to an abelian group, I'm going to call that a matroid valuation if whenever I have a matrix subdivision like this, then the function of the whole matroid should equal the function of the pieces of the subdivision minus the ones of codimension 1 plus the ones of codimension 2, etc. Okay? So for example, well, yeah, so basically ways that behave valuatively with respect to this picture. Okay? So what are some examples of these things? Well, a first obvious example is just the volume of the matrix polytope. That's evaluation. And in a joint paper with Carolina Benedetti in Colombia and Jeff Doker, a student at Berkeley, for example, we managed to find a combinatorial formula for the volume of a matrix polytope. But actually it turns out that this formula is pretty hard to work with. Okay? There's other valuations that you can consider, such as things like the Ehrhart polynomial of the matrix polytope, things like this. One that I would like to mention is the Trop polynomial of the matroid. And the special thing about that one is that that's a function defined in terms of the matroid, not in terms of the polytope. Okay? Now, maybe the main application of these ideas is this theorem of Speyer that gives a bound for the number of faces that a tropical linear space has in each dimension. Okay? And the way this theorem is used is by producing this invariant Gm of t that behaves well under subdivisions, and then just using that guy to obtain some bounds. Okay? But given that we have all of these matrix valuations, the natural question that we can ask is can we systematically produce valuations? Can we understand all of them? What can we say about this? Okay? And so then the next thing I would like to tell you about is just this very general matrix valuation that we constructed with Alex Fink, who's a student at Berkeley, and Felipe Rincon, who at the time was a student in Colombia. Now he's at Berkeley also. So this valuation takes a matroid and produces this formal sum that does the following thing. For each permutation, it tells me the rank of the first element and the rank of the first 2 elements, the rank of the first 3 elements, etc. So just as an example, what is the valuation for the row space of this matrix? Well, you have to do this for every permutation. So for example, if you do it for the permutation 3, 4, 2, 1, then you have to say, okay, the rank of 3 is 1. Then the rank of 3 and 4 is 1. Then the rank of 3, 4, and 2 is 2. Then the rank of 3, 4, 2, and 1 is 2. And you do this for every permutation. You take this formal sum, and so you just get this huge expression. Okay? And so what we show is that this is a matrix valuation. If you think about it, this is actually a little bit surprising. For example, for this subdivision, we would need to have an equation like that one over there. V of m should be equal to that sine sum of the V of all the different matrices that appear in this picture. But if you think about it, each one of those terms is a sum of 6 factorial terms. And so you have this massive cancellation that occurs. So for each permutation, the left-hand side and the right-hand side have to equal each other. Okay? And so here's an example of the kind of calculation of the kind of cancellation that occurs. Okay? And the way we prove that cancellation occurs is that we take that huge sum and we split it up into little sums, and for each one of these little sums, we can interpret this, like one of these little sums, as a reduced Euler characteristic of a contractible space. So we take this huge thing, we split it up into little groups. For each group, we construct a space that has that Euler characteristic, and we prove that it's contractible. That's how we do this. Okay? By the way, this was also done by Harm-Dirksen independently, in an almost equivalent statement was proved by him. And the great news about this is that my student Alex Fink and Dirksen independently proved that actually this matrix evaluation is universal. Okay? And so really, any other matrix evaluation that occurs is a specialization of this one. Okay? And through a little bit of a detailed analysis, they can say for a fixed number of elements and a fixed rank, how many valuations are there. Okay? If V of n comma r is the number of independent matrix evaluations, then they can give a generating function for those guys. Okay? And so, in principle, that means that we know every single matrix evaluation. Okay? But in practice, there is more to do. I mean, this is a universality statement, and then the question becomes, if I have some other matrix evaluation, how do I very explicitly say what it is? Okay. So just to summarize, the main point of my talk again is that we don't really understand tropical varieties very well yet, and we should work harder to do it. In the special case of tropical linear spaces, we do understand some things. Okay? So we know that locally these things are basically matroids, and that theory is very well developed. Globally, they are like matrix subdivisions, and that theory is not well developed yet. And that's something that we're working on. So some of the future directions that we're working on is, like I said, just understanding what these matrix subdivisions can look like. We want to do this because we want to have consequences not only for tropical linear spaces, but in the setups studied by Kaplanov and by Laforgue. And there are things that we can ask, like we think we can interpret these things as mixed subdivisions. We hope that we can build some kind of secondary polytope that parametrizes these different subdivisions. So that's something we're trying to do. A different direction that we're extending this into is extending it to other types. Like I said, you can think of matroids as arising from torus orbits in the Grassmannian, but now you can ask the same thing for other homogeneous spaces. And this is something that I'm working on with Felipe Rincon and Mauricio Velasco, both Colombians at UC Berkeley. And we already have some nice results that say that there is a connection between tropical homogeneous spaces and the theory of Coxeter matroids, which is what you get when you study matroids for other root systems. And of course, the hope is that we could take some of these things and extend them to the general case of tropical varieties. Thank you very much.